Hi, I'm Vaidehi. I'm so excited because today I'm going to tell you all about writing, counting, and converting in binary. Binary is actually the language of computers, but it's really just a number system. And it turns out we actually work with number systems every day. You and I count in the base 10 number system, which is also called denary. Binary is not that different from the base 10 number system. The one exception is that it's the base 2 number system. So in base 10, you use 10 digits to count 0 through 9. But in binary, you can only use 2 digits. The 2 digits you can use are 0 and 1. Now, you might be wondering, if there's a whole number system called binary, and you're supposed to count in it, how do you count beyond 0 and 1? What do you do when you only have 2 digits to work with? Well, it turns out the way you count in binary is the same way that you count in base 10. You just continue to increment the digits until you run out of places. We first start with the first digit, 0, and then we increment it until we filled it up completely. So we'll start with 0 here, then we'll increment it to 1. Now we've run out of possible digits to use. We only have 2 that we can use, 0 and 1. So what happens when we get to 1 and we filled up this digit? Well, we just need to move over to the next place value and reset this digit. It's the same way that when you count in base 10, when you get to the number 9, you reset the number 9 to 0 and add a place value to hit the number 10. So we'll do the same thing in binary here. In binary, once we get to 1, we will reset this digit to 0 and add another digit right here. And we'll continue doing this again. Here, we'll increment this digit so that we have 1s in both place values. Now, we've used up both of these digits, so we'll need to reset both digits and add another place value. We'll keep doing this and fill up all of the possible digits we have. So you might be able to notice that there is a pattern to how I incremented 0s and 1s as we counted through from 0 through 10 in binary. You'll also notice that counting through binary and looking from one number to the next can get a little bit hard at times. Looking at 0s and 1s isn't the most human-friendly way of reading numbers. So we might start to wonder, what are other ways of representing the same numbers? It turns out that binary, while it may be great for computers, isn't so easy for us to understand as humans. So it's helpful to know how to convert between binaries sometimes, or at least be able to convert between binary and something that we understand. So let's look at an example of how to convert between base 10, the number system that we're familiar with, and base 2, the number system that computers use. So before we talk about converting in a bit more depth, let's first remind ourselves about something we may not have thought about in a while since school: the powers of 2. We'll want to look at how the powers of 2 work and remind ourselves of some important numbers because we're going to use them in just a second. Remember that 2 to the power of 0 is 1, 2 to the power of 1 is 2, and as we continue to look at the rest of the powers of 2, notice some important numbers, specifically 256 and 128. We'll want to remember the first few powers of 2. If we can recall them pretty easily, it'll make conversion a little bit easier and faster. So let's take an example of a simple number, like the number 27, and convert it from base 10 into base 2. One thing to note here is that I'm writing 27 with the subscript of 10. All that means is that I'm looking at this number in base 10. This is important to note because we're about to convert between two different number systems from base 10 to base 2. So if you see this number 10 down here, we're just referring to the base. So when we're converting between two numbers, we want to ask ourselves, which power of 2 can I reach without going over my number? And when we're talking about the number here, we're talking about 27. So when we look at the powers of 2, we know that 2 to the power of 5 is 32. So that power of 2 is too big to be used here because 32 is bigger than 27. But 2 to the power of 4 is 16. And 16 is less than 27. So we'll start by using 2 to the power of 4 as we begin converting 27 into its binary representation. Once we find a power of 2 that is smaller than the number we're trying to convert, we actually can subtract it from our number itself. So in this case, 2 to the power of 4 is smaller than 27, and 2 to the power of 4 is 16. Now we have a new number to work with, but we're going to use the same exact technique until we get down to the number 0. So in this case, we're going to look for which power of 2 is less than 11. In this situation, 2 to the power of 3, which is 8, is the only number that's close enough to 11 without going over it. So we'll take 2 to the power of 3, the number 8, and subtract it from 11. Now we're dealing with the number 3. 2 to the power of 1, the number 2, is the closest power of 2 that doesn't go over 3. So we'll continue this pattern again. All right, so now that we have continued this process until we're left with just the number 0, what do we do with this whole subtraction thing that we just did? Well, we can use the powers of 2 that we actually used to subtract in order to find the equivalent binary representation. So we'll notice that each of the powers of 2 and their equivalent versions that we used while subtracting all add up to the number 27. So what do we do with these powers of 2? Well, each of them actually map to a digit in the binary representation of the number 27. Let's take a look to see what that actually means. So, looking at each of our powers of 2 and mapping them to their equivalent binary place value, we'll see that every power of 2 that we actually used gets a 1 in its binary representation. For example, we used 2 to the power of 0 and 2 to the power of 1. So in the 2 to the power of 0 place in the binary representation, we put a 1, and the same goes for 2 to the power of 1. However, we never use 2 to the power of 2, or the number 4, in order to convert. So 2 to the power of 2, the number 4, wasn't used, so 2 to the power of 2 in our binary representation actually just gets a 0. And we'll notice that 2 to the power of 3 and 4, which we both used, also get 1s in their place value in the binary representation. So this means that in order to convert 27 from base 10 into base 2, we can determine that the equivalent version maps to the numbers that we used here. So 27 in base 2 is the same as 11011. So let's look at one more example. I've already drawn this one out, so it should be a little bit easier to see the pattern here. Notice that when we convert the number 114 in base 10 into its equivalent version in binary, base 2, we'll see that in the place values where we've marked a 1 in the binary representation, we actually ended up using the equivalent power of 2 as we subtracted away from the main number 114. So for example, 2 to the power of 5 has a 1 in it, and we did use 2 to the power of 5 32 as we subtracted away from 114 until we got down to the number 0. An interesting thing to note here is that when a base 10 number like 114 is being converted into binary, because it's an even number, it ends in 0. This is in contrast with a number that's odd, like 27, which we saw earlier. When that's converted into binary, the last number, the last digit, is 1 instead of 0. So what happens if we want to convert from binary into base 10? Well, we can take the same logic we just applied and sort of flip it. So for example, here's a number, 10100, which we want to convert into base 10. So we can map the place values that have 1s in them, in this case 2 to the power of 4 and 2 to the power of 2. And we know that because there are 1s, we've used the equivalent of that power of 2. So in this case, we know that 2 to the power of 4 has a 1, so that means we use 16. And 2 to the power of 2 has a 1, which means we use the number 4. The numbers that don't have 1s in them mean that we didn't use that equivalent power of 2, so we can just sum up the numbers that we did use, in this case 16 and 4, and we end up with 20, which is the equivalent of the base 2 representation we started with, 10100. So you might notice an interesting pattern when you start looking at the number of possibilities and the permutations per place value. So for example, when we look at the first 2 bits here, the first 2 binary digits, we know that there are 4 different permutations, 4 possibilities of what we can do with 0s and 1s. This is interesting because this place value is also the same as 2 to the power of 2, which is 4, which maps to the number of possibilities that we have for these 2 digits here. Another interesting thing is that when we use all 8 digits within a byte, we actually have 2 to the power of 8 possibilities, which is 256 permutations. This is interesting because when you have 8 binary digits, you actually have 1 byte. So we can extrapolate to know that 1 byte actually allows us 256 different permutations using just 0s and 1s. So now that you understand how to write, count, and convert in binary, there's just one thing left to say. There's 10 kinds of people in this world, those who understand binary and those who don't. And now you're part of the group that does get it. If you want to keep learning more about binary, head over to Dev2, make an account, and follow me at Vaidehi Joshi. Thanks for watching.
Thanks to Heroku for sponsoring BaseCS. I'm Ben, one of the founders of Dev, and I want to give a shout out to Heroku, the platform that's allowed us to scale from 0 to millions of monthly visitors since we started this venture a few years ago. We rely on Heroku's managed Postgres alongside the rest of their infrastructure to ensure reliability and flexibility as we scale. If you're looking to scale a complex web app without all the chaos, please check out Heroku. Thanks a lot.